Hi guys, welcome to my YouTube channel. Kindly subscribe if you are new here for more videos. Today I want to discuss another topic in discrete mathematics, that is pigeonhole principle. This will help to answer the question when the resources are actually less than the demand. In this one, it's required to use the mapping rule of injection. I want to discuss the mapping rule of injection before actually we get to what the pigeonhole principle states. In discrete mathematics, we have a mapping rule of injection, which is a function that maps distinct element of its domain to distinct element of its codomain. For instance, given two sets, say set A and B, then for a total injection from set A to set B given by the size of A must be less or equal the size of B. This is an equation 1. Suppose that set A is greater than B. The size of set A is greater than B. This will be termed as a contrapositive of equation 1, because we are seeing that in this case each distinct element in set A will not have a distinct element in set B. Now this will be termed as that no total injection in this case from A, no total injection from A to set B. This shows that not everything in set A has a unique arrow to set B. Hence, the explanation of pigeonhole principle. Now, suppose we have 3 baskets which we want to accommodate 4 balls, and each basket must contain a ball. In this scenario, we will be checking Roman 1. We define this with the relevance to the pigeonhole principle, whereby we have the pigeons and we have the holes. So the ball, in this case, the balls are called pigeons, or rather we'll also be calling them items. Number 2, the baskets are called the pigeonholes. So this means we have 3 baskets and we have 4 balls. So assume this is my first basket, I have my second basket, and I have my third basket. I have 4 balls. This is first ball, this is the second ball, third ball, and fourth ball. What we need from this is to define this, which is actually the pigeonholes. These are the pigeonholes, and these are pigeons because they are balls. So we want each we want the exact mapping, so that if we take first ball to the first basket, the second ball to the second basket, that ball to the third basket, you notice that we have one ball that is not accommodated, and therefore we may decide to take this ball to any of this basket. Let me take it to the first basket, such that the first basket here holds 2 balls, the second basket holds 1, and the third basket holds 1 ball. Therefore, the principle states that if n pigeons in m boxes such that n is greater than m, then at least 2 pigeons will be contained in the same box, as we've seen in the scenario up here. This first basket here contains 2 balls. That means that this one will contain 1, this one will contain 1 ball, but we have more pigeons than we have the pigeonhole. And therefore, this pigeonhole principle, the one that states if n pigeons in m boxes such that n is greater than the number of items greater than the number of holes, in this case the baskets, then at least 2 pigeons will be contained in the same box. Now in this topic, we have 3 things that must be defined. One, we have to define 3 things. 1 is the desired output. 2 is the number of items, what we call the pigeons, the number of items, call them pigeons. You need also to define the number of spaces, available, all boxes, all pigeonholes, right? So this one is what we are calling n, this case, and we have m. Now note the desired output. Note the desired output in 1 is defined as the ceiling function, which is given by r is equals to n over m. So this is the desired output, and it's the ceiling function. The ceiling function, one that we've defined, requires one to round up the answer. So the answer that we get will be rounding it up. For example, given n is equals to 4, that's the items or the pigeons, so we can call this one pigeons, and the pigeonholes defined as m is equals to 3, then the desired output will be r is equals to n divided by m, which this one is 4 divided by 3, which is equals to 1.333. Good. So now the ceiling function rounds up to 2. This one, Good. So we have this. Now this states that there is one container or box or pigeonhole that will contain 2 pigeons. At least there is one container that will contain 2 pigeons in it. Note, this ceiling function Nm can be written as n is equals to r minus 1 times m plus 1, this equation 2. Therefore, we will be using this equation 2, to find variable not actually found, using this part here, using equation 1. So thank you guys for joining me. So more of this is coming, so continue subscribing and liking and sending comments. Thank you.